So here's something worth thinking about as you settle in tonight. Reach out and touch whatever's closest to you right now. A pillow, a blanket, the edge of a mattress, maybe a phone, maybe a glass of water on a nightstand. Whatever it is, you're touching a material. Something with a particular texture, a particular weight, a particular way of responding to your fingers. And every single one of those materials has a story. A long, strange, fascinating story about how human beings figured out what the world is made of and then figured out how to make it do extraordinary things. Because here's what's wild. For most of human existence, we had almost no understanding of why materials behave the way they do. We didn't know why some rocks shatter into razor-sharp edges and others crumble into dust. We didn't know why certain metals are soft and others are hard, why glass is transparent, why rubber stretches, why wood burns but stone doesn't. We just worked with what we had, learned by trial and error over thousands of years, and slowly, painstakingly, built a civilization out of stuff we barely understood. The entire arc of human history can be told through materials. In fact, that's exactly how archaeologists organize the past. The Stone Age, the Bronze Age, the Iron Age. We literally name entire eras of human civilization after the materials we'd figured out how to use. Think about what that says. Not the religion we practiced, not the languages we spoke, not the wars we fought, the materials. Because in the end, the materials are what made everything else possible. And that's what we're going to talk about tonight. The whole long, improbable, sometimes accidental, sometimes tragic, often beautiful story of how we went from chipping rocks in a river valley to engineering materials one atom at a time. We'll take it slow, start at the very beginning, and just walk through it together. If you drift off along the way, that's perfectly fine. You'll pick up the thread wherever you come back. And honestly, there's something kind of fitting about falling asleep to a story about materials, because the pillow under your head, the fabric against your skin, the springs or the foam in your mattress, every one of those things exists because someone, somewhere, at some point in history, figured out how to make something the world had never seen before. So let's go back, way, way back. About 3.5 million years ago, somewhere in the Great Rift Valley of Eastern Africa. That's where we find the oldest known stone tools. They're called Lomekwian tools, named after a site in Kenya called Lomekwi, and they're crude, really crude. They're basically rocks that have been smashed against other rocks to create a sharp edge. But crude as they are, they represent something enormous. Some early hominin, not even our species yet, this was long before Homo sapiens, looked at a rock and saw not just a rock, but a potential tool. They saw that the material could be shaped. That's the birth of materials engineering, right there, 3.5 million years ago. A hand, a rock, and an idea. Now, for an incredibly long time, stone was basically all we had. And if you've never really thought about stone as a technology, you might be surprised at how sophisticated it eventually became. Because not all stone is the same. Early toolmakers figured out, through generations of trial and error, that certain kinds of rock are far better for making tools than others. Flint is the classic one. Flint is a form of microcrystalline quartz, and it has this remarkable property called conchoidal fracture. What that means is that when you strike flint in just the right way, it doesn't crumble or break randomly. It fractures in smooth, curved, predictable patterns, producing flakes with edges that can be sharper than a modern surgical scalpel. No exaggeration. Archaeologists have measured the edge thickness of well-made flint blades at less than 1 micron. That's thinner than most steel razor blades. And then there's obsidian. Obsidian is volcanic glass. Literally, glass. Formed when certain types of lava cool so quickly that the atoms don't have time to arrange themselves into a crystal structure. They just freeze in place, disordered, and the result is a material that's amorphous, meaning it has no regular internal structure, and it fractures even more sharply than flint. Obsidian blades have been used in modern experimental surgeries because the edges are so clean, so impossibly thin, that they cause less tissue damage than steel scalpels. An obsidian edge can be just a few nanometers thick. We're talking about a technology developed by Stone Age humans that, in certain narrow respects, still outperforms our modern metals. That's humbling when you think about it. But stone has limits. Serious limits. You can make it sharp, but you can't make it tough. A flint blade will cut beautifully, but drop it on a hard surface and it shatters. You can't bend stone. You can't stretch it. You can't melt it and pour it into a mold. Every tool has to be painstakingly knapped, chipped into shape by hand, one flake at a time. And if you make a mistake, if you take off one flake too many, you can't put it back. Stone is an unforgiving material. It's brittle, it's heavy, and it constrains the kinds of things you can build. For millions of years, those constraints shaped everything about how humans lived, hunted, and made their way in the world. And then, somewhere around 9 or 10,000 years ago, something changed. Humans started experimenting with a completely different kind of material, one that would eventually transform everything: clay, ceramics. The discovery that if you take certain kinds of mud, shape it while wet, and then heat it in a fire, it transforms. It becomes hard, durable, waterproof. It keeps that shape permanently. You've just performed a chemical transformation. The heat drives off water and causes mineral changes in the clay particles that can never be reversed. A pot, once fired, is a new substance. It's not dried mud, it's something else entirely. Pottery shows up in the archaeological record starting around 10,000 years ago, maybe a bit earlier in some places, and it's hard to overstate how important it was. Suddenly you could store food, you could carry water, you could cook things in new ways, boiling, stewing, fermenting. These seem like small domestic details, but they changed nutrition, they changed settlement patterns, they changed population growth. The ability to store grain in ceramic vessels is one of the things that made agriculture viable, and the key insight, the materials insight, was that you could take something soft and shapeable and through the application of heat, lock it into a permanent form. Fire as a tool for transforming materials. That idea, that fire, isn't just for warmth and cooking, but for changing the fundamental nature of stuff. That's one of the most important ideas in human history. Because once you have that idea, once you understand that extreme heat can transform one material into another, you're on a path that leads somewhere extraordinary. You're on a path that leads to metal. Here's what probably happened, and I want to stress the probably. Because nobody was writing any of this down and the archaeological evidence is fragmentary. But the best guess is something like this. Sometime around 7,000 years ago, maybe in Anatolia, maybe in the mountains of what's now Iran, someone built a very hot fire. Maybe they were firing pottery. Maybe they were just burning wood in a pit lined with certain kinds of greenish rocks. And when the fire cooled and they raked through the ashes, they found something strange. Small lumps of a reddish, shiny substance. Something unlike any rock they'd ever seen. Something you could hammer without it shattering. Something that bent instead of breaking. Something that gleamed. Copper. They'd accidentally smelted copper. Now, think about that moment. You're a Neolithic human. You've spent your entire life in a world made of stone, wood, bone, and clay. Those are your materials. Those are the only materials anyone has ever known. And suddenly, there's this new thing, this stuff that came out of a rock when you heated it enough, and it behaves in ways nothing else does. It's malleable. You can beat it into flat sheets. It's ductile. You can draw it into wire. It holds an edge, not as sharp as flint, but an edge you can resharpen just by hammering. It doesn't shatter when you drop it, and you can melt it. You can pour liquid copper into a mold made of clay or carved stone, and it'll take any shape you want. When it cools, that shape is permanent. This is casting, and it unlocked possibilities that stone never could. Complex shapes, repeated identical copies, tools and ornaments that would have been impossible to carve from rock. But copper by itself, for all its wonders, isn't that hard. A pure copper knife dulls quickly. A copper axe head deforms under heavy use. Copper is soft, as metals go, because of something happening at the atomic level that those early metallurgists couldn't possibly have understood. Its crystal structure allows planes of atoms to slide over each other relatively easily. We'll come back to that idea later, because it turns out to be one of the most important concepts in all of materials science. But the point for now is that copper was amazing and limited at the same time, and then someone discovered something that changed everything. Again, probably by accident. Someone, somewhere, maybe in the highlands of what's now Turkey, maybe in the Balkans, maybe independently in several places, melted copper together with a small amount of tin, and the result was bronze, an alloy, a mixture of two metals that has properties neither one has on its own. Bronze is harder than copper, significantly harder. It holds a sharper edge. It's more rigid, more durable, more resistant to wear. And it still has copper's wonderful castability. You can melt it and pour it into molds to make swords, spearheads, shields, helmets, tools, jewelry, vessels, bells, anything. Here's the thing about alloys, and this is one of those ideas that sounds simple, but is actually profound. When you mix two metals together, you don't just get an average of their properties. You get something new, something with its own distinct characteristics. The tin atoms, which are a different size than copper atoms, wedge themselves into the copper crystal structure and make it harder for those planes of atoms to slide. It's like putting pebbles in between layers of playing cards. Suddenly, the deck doesn't slide apart so easily. This is called solid solution strengthening, and it's one of the oldest and most fundamental tricks in metallurgy, even though the first people who did it had absolutely no idea why it worked. They just knew that if you added a bit of that grayish metal from those particular rocks to your copper melt, the resulting metal was better, harder, stronger, more useful. The Bronze Age, which started around 3300 BCE in the Near East, was the first time in history that a material, a human-made material, an engineered alloy that doesn't exist in nature, reshaped civilization on a continental scale. Trade networks sprang up spanning thousands of miles because tin is rare and unevenly distributed. Cyprus had copper, Cornwall in England had tin, Afghanistan had tin, and suddenly these distant places were connected by trade routes because you needed both ingredients to make the metal that everyone wanted. Wars were fought over tin supplies. Empires rose and fell based on access to bronze. The material drove the politics, and this is a pattern you'll see over and over again tonight. A new material doesn't just give people better tools. It reorganizes society. It creates new trade routes, new power structures, new forms of wealth and inequality. Materials aren't just physical objects. They're economic and political forces. And the biggest material revolution in the ancient world was still coming, because bronze, for all its virtues, had a fatal weakness: tin. You needed tin to make bronze, and tin was scarce. If your tin supply got cut off, by war, by a trade route collapsing, by the political chaos that swept across the eastern Mediterranean around 1200 BCE, during what historians call the Bronze Age collapse, then you couldn't make bronze. You were stuck. Unless you could figure out how to work with a different metal, a metal that was everywhere, buried in reddish-brown ore in practically every corner of the earth. A metal that was far more abundant than copper and tin combined. A metal that, if you could master it, would make bronze obsolete. Iron. And iron, it turns out, is a completely different beast from copper or bronze. And the reason comes down to one deceptively simple fact. Iron has a much higher melting point. Copper melts at about 1085 degrees Celsius. Tin melts at a mere 232. You can melt both of them in a well-built charcoal furnace. But iron? Iron melts at 1538 degrees Celsius. And for most of human history, nobody could build a fire that hot. Not even close. The charcoal furnaces of the Bronze Age topped out well below iron's melting point. So you couldn't smelt iron the way you smelted copper. You couldn't just heat the ore until the metal ran out as a liquid. Iron demanded a completely different approach, and figuring that approach out took centuries of experimentation, failure, and slow, incremental progress. What early iron workers learned to do was build a structure called a bloomery. It's basically a chimney-shaped furnace made of clay, with a hole at the bottom for air. You'd fill it with alternating layers of iron ore and charcoal, light the charcoal, and then pump air through the bottom using bellows, usually animal skin bags that you'd squeeze by hand or with your feet, forcing a blast of air into the furnace to make the charcoal burn hotter. And here's what happened inside. The charcoal wasn't just fuel, it was also a chemical agent. When charcoal burns in a restricted air supply, it produces carbon monoxide, and carbon monoxide is a reducing agent. It strips the oxygen away from the iron oxide in the ore, leaving behind metallic iron. But because the temperature never got high enough to melt the iron, what you got wasn't a pool of liquid metal. What you got was a spongy, porous lump of iron mixed with slag, a glassy waste material formed from the impurities in the ore. This lump was called a bloom, and it was a mess. Full of holes, full of trapped slag, and completely useless in that state. To make it into something usable, you had to take that bloom out of the furnace while it was still glowing hot and beat it. Hammer it. Again and again and again. Fold it, hammer it, fold it again. Each blow squeezed out a little more slag, closed a few more pores, welded the iron particles together. This is wrought iron, iron that has been wrought, meaning worked, by hand. And it's a brutally labor-intensive process. Making a single iron tool required hours of hammering at a forge, and the resulting metal was softer than bronze. That's right. The first iron tools were actually inferior to the bronze ones they were meant to replace. Early wrought iron is fairly soft, about the same hardness as copper, and it doesn't hold an edge as well as good bronze. So why bother? Why would anyone switch from bronze to this difficult inferior metal? The answer is availability. Iron ore is everywhere. You don't need rare tin from distant mines. You don't need trade networks spanning continents. Almost any community can find iron ore nearby, and that changes the economics of metal completely. When the Bronze Age trade networks collapsed around 1200 BCE, and the reasons for that collapse are still debated, but it involved a combination of invasions, earthquakes, droughts, and cascading political failures across the eastern Mediterranean. Suddenly the tin stopped flowing. Bronze became scarce, and iron, crude and difficult as it was there. It was available, and necessity, as it always does, drove innovation. The Hittites, who controlled a powerful empire in Anatolia, that's modern-day Turkey, are often credited as the first major ironworking civilization, though the real picture is more complicated than that. There's a famous theory that the Hittites kept ironworking as a closely guarded state secret, using their monopoly on iron weapons as a military advantage. The evidence for this is mixed. There are Hittite texts that mention iron and suggest it was considered precious, but whether they truly had a monopoly is debated among historians. What is clear is that after the Hittite Empire fell, around 1180 BCE, iron-working knowledge spread rapidly across the Near East, into Africa, into Europe, and into South Asia. The Iron Age had begun. And here's where the story gets really interesting, because what happened next wasn't just a switch from one metal to another. It was the discovery that iron could be transformed into something much, much better: steel. Now, steel is not a separate metal from iron. Steel is iron with a little bit of carbon dissolved in it, typically between about 0.2 and 2.1% carbon by weight. That's it. That tiny amount of carbon changes everything. It makes the iron dramatically harder, stronger, and better at holding a sharp edge. And the reason, again, comes down to what's happening at the atomic level. Carbon atoms are small, much smaller than iron atoms, and they fit into the gaps between iron atoms in the crystal structure, like tiny wedges. They pin the crystal planes in place, making it much harder for them to slide over each other. More carbon, up to a point, means more hardness, but also more brittleness. And that trade-off, hardness versus toughness, is one of the central tensions in all of materials engineering. We'll see it everywhere tonight. Early ironworkers stumbled onto steelmaking without understanding any of this chemistry. What they figured out, through generations of practice, was that if you kept iron in contact with charcoal at high temperatures for long enough, the iron changed. It became harder. It took a better edge. What was actually happening was carbon from the charcoal diffusing into the surface of the iron, a process we now call carburization or case hardening. The Smiths didn't know about carbon atoms. They didn't know about crystal structures. They just knew that certain techniques, passed down from master to apprentice, produced better metal. And this is where one of the most legendary materials in history enters the picture: Wootz steel, sometimes called crucible steel. It originated in South Asia, probably in what is now southern India and Sri Lanka, and the earliest evidence for it dates back to around 400 BCE, maybe earlier. The process involved sealing small pieces of iron together with carbon-rich materials, wood, leaves, sometimes specific plants, in a small clay crucible, then heating the whole thing in a furnace until the iron actually melted. This is remarkable, because remember, iron melts at 1,538 degrees, but the carbon lowered the melting point. That's what carbon does in iron. It acts as a flux, reducing the temperature needed to liquefy the metal. The result was a small ingot of high-carbon steel that had been completely melted and re-solidified, which meant the carbon was uniformly distributed throughout, not just on the surface. Wootz steel ingots were traded across the ancient world. They traveled from India to the Middle East along maritime and overland trade routes, and in the workshops of Damascus, Syrian swordsmiths forged them into blades of legendary quality. These are the famous Damascus steel swords, and their reputation was extraordinary. They were said to be hard enough to cut through a European sword and flexible enough to bend without breaking. The blades had a distinctive wavy, water-like pattern on their surface, called a damask pattern, that was both beautiful and mysterious. For centuries, European metallurgists tried and failed to replicate it. And here's what's fascinating from a materials science perspective. Modern analysis of surviving Damascus steel blades has revealed something remarkable. The wavy pattern is created by bands of different microstructures within the steel, alternating layers of hard iron carbide particles, called cementite, embedded in a softer iron matrix. In some blades, researchers have even found carbon nanotubes and cementite nanowires, nanostructures that we consider cutting-edge materials science today, formed accidentally in medieval forges by swordsmiths who had no concept of nanotechnology. The specific combination of trace impurities in the Indian ore, the carbon-rich materials used in the crucible process, and the forging techniques of the Damascus smiths created conditions that happened to produce nanoscale structures. Nobody designed them. Nobody understood them. They just emerged from a process refined over centuries of craft knowledge. The secret of Damascus steel was eventually lost, probably in the 18th century, likely because the specific ore deposits with the right trace elements were depleted. Modern metallurgists have gotten close to reproducing it, but the exact historical process remains a subject of research and debate. Meanwhile, Chinese metallurgists were taking iron in a completely different direction. By the 5th century BCE, China had furnaces hot enough to fully melt iron, producing cast iron, iron with a high carbon content that could be poured into molds. Cast iron is very hard and excellent in compression, though brittle under impact. But for plowshares, cooking pots, and architectural elements, it was superb. By the Han Dynasty, around the 2nd century BCE, China had a state-run cast iron industry more than 1,500 years before Europe achieved anything comparable. They even developed techniques for decarburizing cast iron to produce something closer to steel. Materials technology doesn't advance uniformly across the world. It never has. And speaking of swords, since they're such a compelling window into materials science, let's talk for a moment about Japanese sword making, because it illustrates another fundamental materials concept beautifully. The Japanese katana is famous as one of the finest edged weapons ever made, and the process of making one is extraordinary. Japanese swordsmiths started with tamahagane, a type of steel produced in a tatara furnace, a large clay furnace that burned for days, smelting iron sand with charcoal. The resulting bloom contained steel of varying carbon contents, and the smith's first job was to sort through the broken-up bloom, selecting pieces of high-carbon and low-carbon steel by eye and by how they fractured. Then came the folding. The selected steel was heated, hammered flat, folded over, and hammered flat again. This process was repeated many times, traditionally around 15 folds, which creates over 30,000 layers, though the exact number varied by smith and tradition. Each fold welded the layers together and distributed the carbon more evenly, removing impurities and slag in the process. But here's the really clever part. The final blade was constructed from different types of steel in different positions. A hard, high-carbon steel formed the edge, the part that needed to be sharp. A softer, lower-carbon steel formed the spine, the part that needed to absorb impact without breaking. Some constructions used 3, 4, even 5 different steels, each chosen for its specific properties and placed where those properties were most needed. And then there was the quenching, the differential hardening. The smith coated the blade with a mixture of clay, ash, and other materials, thicker along the spine and thinner along the edge. When the blade was heated to a critical temperature and plunged into water, the thin-coated edge cooled rapidly, forming a very hard but brittle crystalline structure called martensite. The thick-coated spine cooled slowly, retaining a softer, tougher structure called pearlite. The result was a blade that was hard where it needed to cut, and flexible where it needed to survive impact. And the boundary between the two zones, that distinctive wavy line you see on a katana blade, called the hamon, is the visible signature of this differential heat treatment. It's where two different crystal structures meet inside the same piece of steel. This is materials engineering at its most elegant, done entirely through empirical knowledge, without any understanding of atomic structure or phase diagrams or crystallography. Japanese swordsmiths were manipulating the microstructure of steel hundreds of years before the word microstructure existed. They were exploiting phase transformations in iron-carbon alloys centuries before anyone knew what a phase transformation was. And that pattern, practical mastery running centuries ahead of theoretical understanding, is one of the great themes of materials history. For thousands of years, people made extraordinary things with materials they didn't understand. The theory, when it finally came, often just explained what craftspeople had already figured out through generations of patient, hands-on experimentation. There's a humility in that, I think, a reminder that knowledge doesn't always flow from theory to practice. Sometimes it flows the other way. But theory was coming, and when it arrived, when people finally started to understand why materials behave the way they do, it would unleash a revolution in materials that would reshape the entire world in a matter of decades. But first, there was a more immediate revolution happening, an industrial one. And it started, as so many things in this story do, with someone solving a practical problem. Let's talk about Henry Bessemer. It's the 1850s, and the world runs on wrought iron and cast iron. Wrought iron is tough but soft. Cast iron is hard but brittle. Steel, real steel, the good stuff with just the right amount of carbon, is known, it exists, but it's incredibly expensive to produce. Making steel the old way, the crucible method, involved melting small batches of iron and carbon in sealed clay pots for hours. You'd get a few kilograms at a time, enough for a watch spring, maybe a scalpel, a high-quality tool, not enough for a railroad rail, a bridge beam, a ship hull. The world desperately needed cheap steel, and nobody knew how to make it. Bessemer was an English inventor, born in 1813 in Charlton, Hertfordshire. He was prolific. Over the course of his career, he filed more than 100 patents on everything, from sugar refining to typesetting. But the invention that made his name, the one that arguably did more to shape the modern world than any other single technological innovation, was the Bessemer process for making steel. Here's the problem he was trying to solve. In 1854, during the Crimean War, Bessemer designed a new type of spinning artillery shell that was more accurate than conventional projectiles. But when the French military tested it, the cast iron cannons couldn't handle the increased pressure. They cracked. The guns were too weak for the ammunition. What was needed was a stronger material for the gun barrels, steel. But steel was too expensive to make cannons from. So Bessemer set about finding a way to make steel cheaply and in large quantities. And here's the thing that's really clever about what he came up with. The insight is almost counterintuitive. To make steel from pig iron, that's the crude, high-carbon iron that comes out of a blast furnace, you need to remove most of the carbon. The pig iron has too much, typically around 4%. Steel needs somewhere between 0.2 and 1.5%, depending on what kind of steel you want. The traditional way to remove carbon was to heat the iron in a puddling furnace for hours, stirring it by hand, letting the carbon slowly burn off. It was labor-intensive, slow, and limited in scale. Bessemer's idea was to blow air directly through the molten iron. That's it. Take molten pig iron, blast air through it from below, and the oxygen in the air will react with the carbon dissolved in the iron, burning it off as carbon dioxide. It sounds almost too simple. But here's what happened when Bessemer first tried it, in 1856, in a specially designed converter, a large, pear-shaped vessel with holes in the bottom for the air blast. The reaction was spectacular. When the cold air hit the molten iron, the carbon burned off so violently that the temperature of the metal actually increased. The reaction was exothermic. It produced heat, so much heat that no external fuel was needed to keep the iron molten. The carbon was burning itself out, and the energy released by that combustion kept the metal liquid. The whole process took about 20 minutes. 20 minutes to convert a batch of pig iron into steel. The puddling process took hours to produce a fraction of the amount. Bessemer announced his process to great fanfare in 1856, and then immediately ran into problems. The steel produced by his converters was often brittle and unreliable. It cracked. It was full of blowholes. Customers complained. Steelmakers who had licensed his process demanded their money back. Bessemer's reputation took a serious hit. What had gone wrong? It took a while to figure out, but the issue was phosphorus. Many iron ores contain phosphorus as an impurity, and the Bessemer process, as originally designed, couldn't remove it. Phosphorus in steel is devastating. Even tiny amounts make the metal brittle, especially when it's cold. This is called cold shortness, and it was ruining Bessemer steel made from phosphorus-rich ores. The process worked beautifully with low phosphorus ores, which happened to be the kind Bessemer had used in his initial experiments. But most of the iron ore in Europe and the eastern United States was high in phosphorus. Now, here's where other people enter the story, because the history of materials is never about just one person. Robert Mouchet, a British metallurgist from the Forest of Dean, figured out a crucial improvement. He discovered that adding a small amount of a compound called Spiegeleisen, a manganese-rich iron alloy, to the steel at the end of the Bessemer blow could solve several problems at once. The manganese combined with sulfur, another troublesome impurity, and also helped deoxidize the steel, removing the dissolved gases that were causing the blowholes. This made the steel sound and workable. Mouchet never received proper credit or compensation for this contribution during his lifetime, despite the fact that it made the Bessemer process commercially viable. He died in relative obscurity. That's a common story in the history of materials. The person who gets the patent, and the fame isn't always the person who made the critical contribution. The phosphorus problem was eventually solved by Sidney Gilchrist Thomas, a young London police court clerk who studied chemistry in his spare time. In 1878, Thomas figured out that if you lined the Bessemer converter with a basic material, dolomite or limestone, instead of the acidic silica lining Bessemer used, the basic lining would react with the phosphorus and remove it from the steel. This was the Thomas process, sometimes called the basic Bessemer process, and it opened up vast deposits of phosphorus-rich iron ore that had previously been useless for steelmaking. The iron ores of Lorraine, of Luxembourg, of the English Midlands, suddenly all of them could make steel. Thomas was only 35 when he died of tuberculosis in 1885, just 7 years after his breakthrough. He didn't live to see the full impact of what he'd done, but the impact was enormous. Between the original Bessemer process, Mouchet's manganese addition, and Thomas's basic lining, the cost of steel collapsed. In 1856, steel cost about 50 pounds per ton, roughly 10 times the price of wrought iron. By the 1880s, the price had fallen to 6 or 7 pounds per ton. Steel went from a luxury material to a commodity. And when a fundamental material becomes cheap, everything changes. And this is where Andrew Carnegie enters the picture. Carnegie was a Scottish immigrant who arrived in Pittsburgh as a penniless 12-year-old and worked his way up through the railroad industry. He was ferociously ambitious and had an almost preternatural instinct for where the money was going next. And when the Bessemer process made cheap steel possible, Carnegie saw the future before almost anyone else. He built the Edgar Thomson Steel Works in Braddock, Pennsylvania, in 1875, naming it after the president of the Pennsylvania Railroad, a shrewd bit of flattery toward his biggest potential customer. And Carnegie did something that most steelmakers of the time didn't do. He hired chemists. He brought in scientists to analyze his raw materials, control his processes, and optimize his product. "What's the use of chemistry at a steelworks?" a competitor once asked. Carnegie's answer, essentially, was, "Ask me again in 10 years, when I've driven you out of business." And he did. Carnegie's relentless focus on efficiency, cost-cutting, and reinvestment in technology allowed him to undercut every competitor. By the 1890s, the Carnegie Steel Company was producing more steel than all of Great Britain combined. When he sold the company to J.P. Morgan in 1901 for $480 million, the equivalent of something like $15 billion today, it became the centerpiece of United States Steel Corporation, the first billion-dollar company in the world. And all of that steel went somewhere. It went into railroad rails, thousands and thousands of miles of them, connecting the American continent. It went into bridges. The Brooklyn Bridge, completed in 1883, was one of the first major structures to use steel wire cables. Though its engineer, Washington Roebling, fought a long and painful battle with the quality of the steel supplied by a contractor who was secretly substituting inferior iron wire. Roebling discovered the fraud and had to reinforce the cables with additional wires. But the episode illustrates a critical point about materials. The material itself is only as good as the quality control behind it. A bridge doesn't care about your intentions. It only cares about what you actually built it from. Steel went into buildings. The home insurance building in Chicago, completed in 1885, is often cited as the first steel-frame skyscraper. Before steel frames, the height of a building was limited by the load-bearing walls. The walls themselves had to support all the weight above them, and the taller the building, the thicker the ground floor walls had to be. At a certain height, the walls at the base would need to be so thick that there'd be almost no usable space inside. Steel frames changed the equation completely. The frame carried the load. The walls became mere curtains. Thin enclosures hung on the outside of the frame. And because steel is so strong relative to its weight, its strength-to-weight ratio is vastly better than stone or brick. You could go much, much higher. Within a decade, the skylines of Chicago and New York were being transformed. The Woolworth Building, finished in 1913, rose to 792 feet. The Chrysler Building in 1930, 1,046 feet. The Empire State Building in 1931, 1,454 feet. All made possible by structural steel. And then there's the Eiffel Tower. Gustave Eiffel's tower for the 1889 World's Fair in Paris was actually made of puddled iron, not steel, and yet it demonstrated what was possible with metal structures. At 1,083 feet, it was the tallest structure in the world for 41 years. The entire iron structure weighs about 7,300 metric tons, but if you melted it down and poured it into a cube the size of the tower's base, that cube would be only about 6 centimeters tall. The tower is almost entirely air. It stands because Eiffel understood something crucial about structural materials. It's not just about strength, it's about how you arrange the material. The lattice structure distributes forces so efficiently that the pressure the tower exerts on the ground is no more than the pressure a person sitting in a chair exerts on the seat. Let me mention one more steel story from this era, because it's too good not to tell, and it introduces a material you encounter every single day: stainless steel. In 1913, a metallurgist named Harry Brearley, working in Sheffield, England, which had been the center of the English steel industry for centuries, was trying to develop better steel alloys for gun barrels. He was experimenting with chromium, adding different amounts of it to steel, and testing the results. Most of his experimental samples were failures. He tossed them into a scrap pile in the corner of his lab, and weeks later, he noticed something. Most of the samples in the scrap pile had rusted, as you'd expect steel to do. But some of them hadn't. Some of them were still shining. He pulled them out and checked his notes. The ones that hadn't rusted were the samples with higher chromium content, roughly 12% or more. What was happening? The chromium was reacting with oxygen in the air to form a thin, invisible layer of chromium oxide on the surface of the steel. This layer was incredibly thin, just a few nanometers, but it was stable, non-porous, and self-healing. If you scratched it, the chromium in the steel would immediately react with oxygen to reform the protective layer. The steel was, in effect, protecting itself. It was stainless. Brearley realized the potential almost immediately. This wasn't the right steel for gun barrels. It was too soft for that purpose. But it was perfect for cutlery. Sheffield was already famous for its knives and forks, and stainless steel meant knives that wouldn't rust, wouldn't stain, wouldn't taint the flavor of food. He partnered with a local cutler named Ernest Stewart, and they started producing stainless steel knives in 1914. Today, stainless steel is everywhere. Your kitchen sink, surgical instruments, food processing equipment, architectural cladding, chemical tanks, watch cases, elevator doors. It's one of the most important alloys ever developed, and it was discovered essentially by accident, by a man who noticed that some of his failed experiments weren't rusting. But here's what strikes me about all of these stories. Bessemer and Mouchet and Thomas and Carnegie and Brearley. They were all working empirically. Trial and error. Mix this with that, heat it up, see what happens. They had very little understanding of why their materials behaved the way they did. The atomic structure of metals was unknown. Crystal structures were unknown. The mechanisms of hardness and brittleness were completely mysterious. Materials science, as a discipline, barely existed, and yet these people built the modern world. But the question remained, hanging in the air like an unanswered puzzle. Why? Why is steel harder than iron? Why does chromium prevent rusting? Why does quenching a blade in water make it hard? Why does anything behave the way it does? And to answer those questions, to move from craft knowledge to true scientific understanding, someone needed to figure out how to look inside a material, to see its hidden structure, to understand what's happening at a scale far too small for any eye to see. And that's exactly what happened at the turn of the 20th century, when a father and son in England pointed a beam of invisible radiation at a crystal and changed everything we thought we knew about the solid world around us. X-rays had been discovered in 1895 by Wilhelm Röntgen, a German physicist who noticed that a mysterious radiation from his cathode ray tube was causing a fluorescent screen across the room to glow. He didn't know what the rays were. That's why he called them X-rays, X for unknown. But he quickly realized they could pass through solid materials and create shadow images on photographic plates. Within weeks of his announcement, doctors were using X-rays to see broken bones. The medical applications were obvious and immediate, but the application that would transform materials science took a little longer to arrive. The key question was, what exactly are X-rays? Are they particles? Are they waves? If they're waves, what's their wavelength? By the early 1910s, physicists had established that X-rays were electromagnetic waves, like light, but with a much shorter wavelength, on the order of angstroms, which is about the size of an atom. And here's where a German physicist named Max von Laue had a beautiful idea. If X-rays have wavelengths similar to the spacing between atoms in a crystal, then a crystal should act like a diffraction grating for X-rays. Waves diffract. They bend and interfere with each other when they encounter obstacles spaced at about the same scale as their wavelength. You can see this with visible light passing through a finely ruled grating. Laue reasoned that if atoms in crystals are arranged in regular, repeating patterns, then X-rays passing through a crystal should produce a diffraction pattern, and in 1912, he proved it. He shot X-rays through a crystal of copper sulfate and captured the resulting pattern on a photographic plate. Instead of a smear, he got a symmetric pattern of distinct spots. The crystal was diffracting the X-rays, and the arrangement of those spots contained information about the arrangement of atoms inside the crystal. This was huge. For the first time in history, humans could see, indirectly, through the language of diffraction patterns, how atoms are arranged inside solid materials. And the people who turned this technique into a practical tool for understanding materials were a father-son team in England, William Henry Bragg, and his son William Lawrence Bragg. Now, the younger Bragg, Lawrence, as he was called, was just 22 years old when he worked out the mathematical relationship that made X-ray crystallography practical. In 1913, he derived what we now call Bragg's law, which relates the angle at which X-rays are diffracted to the spacing between planes of atoms in the crystal. The equation is elegant and simple. N times lambda equals 2 times d times sine theta. Lambda is the wavelength of the X-rays. D is the distance between atomic planes. Theta is the angle of incidence. And n is a whole number, the order of diffraction. If you know the wavelength of your X-rays, and you measure the angles at which you get strong diffraction peaks, you can calculate the spacing between the atoms. You can determine the crystal structure. Lawrence Bragg won the Nobel Prize in Physics for this in 1915, alongside his father. He was 25 years old, and to this day, he remains the youngest person ever to win a Nobel Prize in Physics. And the tool he helped create, X-ray crystallography, went on to become one of the most important analytical techniques in science. It's the same technique that would later be used to determine the structure of DNA. But its first and most immediate application was in understanding the structure of metals and minerals, and what it revealed was astonishing. Here's what they found. The atoms in metals aren't just randomly jumbled together. They're arranged in highly regular, repeating three-dimensional patterns called crystal lattices. Think of it like stacking oranges in a box. If you carefully arrange them, each orange nesting into the gaps between the ones below, you get a regular, repeating structure. Atoms in metals do the same thing, and there are several different ways they can pack together. Iron at room temperature, for instance, forms a body-centered cubic structure. Imagine a cube with an atom at each corner, and one atom right in the center. Copper and aluminum form face-centered cubic structures, atoms at each corner and one in the center of each face of the cube. These different arrangements have profound consequences for how the metal behaves. And here's where things get really interesting. In theory, if a metal crystal were perfect, every atom in exactly the right position, the lattice extending flawlessly in all directions, that metal should be incredibly strong. Calculations based on the forces between atoms predicted that a perfect iron crystal should have a tensile strength of about 13,000 megapascals. The actual tensile strength of ordinary iron, about 200 megapascals, less than 2% of the theoretical value. Something was making real metals vastly weaker than they should be. But what? The answer came in 1934, when three scientists working independently, Geoffrey Ingram Taylor in England, Egon Orowan in Hungary, and Michael Polanyi in Germany, proposed the concept of dislocations. A dislocation is a line defect in the crystal lattice. Imagine all those neatly stacked atoms, and now imagine that somewhere in the middle of the crystal, one row of atoms just ends. The atoms above the end of that row are slightly out of position. The atoms below are slightly out of position, and there's a line of distortion running through the crystal where the extra half row terminates. Here's why dislocations matter so much. When you apply a force to a metal, trying to deform it, you don't need to simultaneously slide an entire plane of atoms over the plane below, which would require enormous force, enough to break all those atomic bonds at once. Instead, the dislocation moves. It's like a wrinkle in a heavy carpet. If you want to slide the whole carpet across the floor, you'd need enormous force. You'd have to overcome the friction of the entire carpet at once. But if you make a wrinkle at one edge and push it across, the carpet moves with much less effort. The wrinkle concentrates the motion into a small area, so you only need to overcome friction at the wrinkle, not across the whole carpet. That's what dislocations do in metals. They allow deformation to happen one small step at a time instead of all at once. And that's why real metals are so much weaker than perfect crystals would be. They're full of dislocations, and those dislocations move easily. But, and here's the clever part, if you can make dislocations harder to move, you can make the metal stronger. And suddenly, all those old tricks of the blacksmith have a scientific explanation. Why does alloying make metals harder? Because foreign atoms in the crystal lattice create stress fields that impede dislocation motion. Why does cold working, hammering a metal, make it harder? Because the hammering creates more and more dislocations, and when there are too many, they get tangled up with each other and can't move freely. It's like a traffic jam. A few cars on the road move easily, but pack the road and nothing moves. Why does annealing, heating the metal and cooling it slowly, make it soft again? Because the heat gives atoms enough energy to rearrange, the dislocations untangle, and the crystal structure relaxes. And heat treatment. The whole science of heat-treating steel, which blacksmiths had practiced empirically for millennia, suddenly made sense in terms of crystal structures and phase transformations. Let me walk you through what happens when you heat-treat a piece of steel, because it's a beautiful example of how a material can be completely transformed without changing its chemical composition at all. Steel is iron with carbon. At room temperature, the carbon atoms sit in specific positions in the iron crystal lattice. But here's the thing. Iron changes its crystal structure when it's heated. Below 912 degrees Celsius, iron has a body-centered cubic structure, which is called ferrite. Above 912 degrees, it switches to a face-centered cubic structure, called austenite. And the face-centered cubic structure has bigger gaps between the atoms, which means it can dissolve much more carbon. So when you heat steel above 912 degrees, the carbon that was reluctantly squeezed into the tight body-centered cubic structure suddenly has room to spread out and dissolve evenly throughout the austenite. Now, if you cool that steel slowly, let it sit in the furnace and gradually come back to room temperature, the austenite converts back to ferrite, and the carbon comes out of solution in an orderly way, forming alternating layers of iron and iron carbide in a beautiful laminar structure called pearlite. If you look at pearlite under a microscope, it looks like a fingerprint, concentric bands of light and dark. Pearlite is the microstructure of ordinary medium carbon steel, and it has a nice balance of hardness and toughness. But if you cool that steel rapidly, if you quench it, plunging it from austenite temperature straight into water or oil, something completely different happens. The carbon atoms don't have time to diffuse out and form orderly layers. The crystal structure tries to switch from face-centered cubic back to body-centered cubic, but the trapped carbon atoms distort the lattice, forcing it into a strained, elongated structure called body-centered tetragonal. This is martensite, and it's extremely hard. The trapped carbon atoms act like millions of tiny wedges, pinning every dislocation in place, making the metal rigid and resistant to deformation. Martensite is what gives a quenched blade its hardness. It's also very brittle. Those trapped atoms create internal stresses that make the metal prone to cracking. That's why you temper the blade afterward. Tempering means reheating it to a moderate temperature, typically between 150 and 650 degrees Celsius, depending on what properties you want, and holding it there for a while. This allows some of the trapped carbon to diffuse out and form tiny carbide particles, relieving some of the internal stress. The martensite partially transforms into a softer, tougher structure. The higher the tempering temperature, the more carbon comes out, and the softer and tougher the steel becomes. So the blacksmith's art, quench it hard, then temper it back to the right balance, is really a precise manipulation of crystal structures and carbon diffusion. It's materials science, performed by hand, in a forge. And once scientists understood this, once they could see crystal structures with X-rays, and explain mechanical behavior with dislocation theory, and map phase transformations on equilibrium diagrams, they could start designing materials with specific properties. Not just stumbling onto good alloys by accident, but actually predicting what would happen if you added this element in that amount and heat-treated it this way. Materials science became a science, not just a craft. This understanding also explained something that had puzzled people for centuries: why metals behave so differently from ceramics and glass. Metals bend. Ceramics shatter. Why? It comes down to the nature of the atomic bonds. In metals, the bonding is metallic. The outer electrons are shared among all the atoms in the structure, forming what's sometimes called an electron sea. This allows planes of atoms to slide over each other without breaking the bonds, because the electrons just redistribute. That's why metals are ductile and malleable. In ceramics, the bonding is ionic or covalent. Electrons are locked between specific pairs of atoms, forming rigid, directional bonds. When you try to deform a ceramic, you can't slide the plane smoothly because the bonds resist being rearranged. Instead, the material just cracks. The bonds break catastrophically, rather than accommodating the motion. Glass is another fascinating case. It looks solid, feels solid, but its internal structure is completely different from a crystal. The atoms are arranged in a disordered, amorphous pattern, frozen in the random arrangement of a liquid. There's no crystal lattice, no regular planes of atoms, and therefore no dislocations, which is why glass doesn't bend. When you apply enough stress, it doesn't yield, it shatters, catastrophically, with cracks propagating at thousands of meters per second. And yet glass is one of the most versatile materials in human history. It's transparent, because its amorphous structure doesn't have the regularly spaced planes that would scatter light through diffraction. It can be formed into almost any shape when molten. It's chemically inert, and its properties can be tuned dramatically by changing its composition. Add boron for heat resistance, lead oxide for brilliance, specific metal oxides for color. The modern glass industry was transformed by the float glass process, developed by Sir Alistair Pilkington at Pilkington Brothers in St. Helens, England, in 1959. The idea is elegant. Molten glass is poured onto a bath of molten tin. Because glass is less dense than tin, it floats, and the liquid tin surface is perfectly flat. So the glass spreads into a sheet with perfectly flat, parallel surfaces, no grinding or polishing needed. Today, virtually all flat glass in the world is made by the float process. But I've gotten ahead of myself, because there's another material we haven't talked about yet, one that's arguably even more important than steel or glass in shaping the built environment of the modern world. A material so ubiquitous, so taken for granted, that you probably don't even think about it, but it's holding up the building you're in right now. It's under the road you drove on today. It's in the sidewalks and the bridges and the dams and the foundations of almost everything around you. Concrete. And concrete has its own extraordinary story, one that starts with the Romans, and with a mystery that took 2,000 years to solve. The Pantheon in Rome was built around 125 CE, and its dome, an unreinforced concrete dome spanning 43.3 meters, remains the largest unreinforced concrete dome in the world, 2,000 years later. Think about that. Nobody has built a bigger unreinforced concrete dome than the one the Romans poured 19 centuries ago, and Roman concrete is still standing. Harbors, aqueducts, foundations, many have survived 2 millennia. Meanwhile, modern concrete often deteriorates after 50 years. The secret was in the recipe. Roman concrete used volcanic ash, called pozzolana, which reacted with lime and seawater to form minerals that actually strengthen the material over time. Researchers found that seawater, instead of degrading Roman marine concrete, dissolved ash particles and formed crystals that filled cracks and reinforced the structure. The Romans had accidentally created a self-healing concrete. When the Roman Empire fell, this practical knowledge was lost. For over 1,000 years, nobody in Europe made concrete that came close to Roman quality. It came back in the 18th century, when a British engineer named John Smeaton was tasked with rebuilding the Eddystone Lighthouse off the coast of Plymouth, England. The previous wooden lighthouses had been destroyed, one by a storm, one by fire. Smeaton needed a material that could withstand the relentless pounding of Atlantic waves. He experimented with different limes and different additives, and he found that a mixture of lime with a specific kind of clay produced a cement that would set and harden even underwater. This was hydraulic cement, and Smeaton's discovery, published in 1791, kicked off a new era of cement chemistry. But the real breakthrough came in 1824, when a bricklayer from Leeds named Joseph Aspdin patented what he called Portland cement. He named it that because the hardened cement resembled Portland stone, a prestigious limestone used in many of London's finest buildings. Aspdin's process involved heating a mixture of finely ground limestone and clay to high temperatures in a kiln, producing a klinite, a hard, nodular material that, when ground to a fine powder and mixed with water, would set into a hard, stone-like mass. Now, Aspdin's original product wasn't quite what we use today. Modern Portland cement requires heating the raw materials to a higher temperature, about 1,450 degrees Celsius, to produce the specific calcium silicate compounds that give it its strength. This refinement came through the work of Aspdin's son, William, and others over the following decades. But the basic principle was established. You could manufacture a powder that, when mixed with water and aggregates like sand and gravel, would harden into something as durable as rock, and you could shape it into anything you wanted before it set. Let me tell you how concrete actually works, because it's genuinely fascinating, and most people have never thought about it. When you mix Portland cement powder with water, a chemical reaction called hydration begins. The calcium silicates in the cement react with water to form calcium silicate hydrate, often abbreviated CSH, which grows as a tangled network of tiny, hair-like crystals. These crystals interlock and bind together, trapping the water and forming a rigid structure. It's like a microscopic forest of crystal needles growing and tangling around each other, getting denser and stronger over time. The process takes weeks to reach most of its strength, but it actually continues for years. Concrete at 28 days, the standard testing age, is typically only at about 85 to 90% of its ultimate strength. It keeps getting stronger, slowly, as more of the cement hydrates. Here's the key thing about concrete's mechanical properties. Concrete is incredibly strong in compression. A typical structural concrete can handle compressive stresses of around 30 to 50 megapascals. That's roughly 4,000 to 7,000 pounds per square inch. You can stack enormous weight on top of it, but its tensile strength, its resistance to being pulled apart, is terrible. Only about 1/10 of its compressive strength. Concrete can bear the weight of a building, but if you try to bend it, the side that's being stretched will crack almost immediately. This is why reinforced concrete, was such a transformative invention? The idea is simple. Embed steel bars, rebar, inside the concrete. The steel handles the tension, the concrete handles the compression, and together they can handle forces that neither could manage alone. The concept emerged from several inventors working in parallel in the mid-19th century. Joseph Monnier, a French gardener frustrated by cracking planters, patented reinforced concrete in 1867. François Hennebeek developed a comprehensive building system in the 1890s. And there's a beautiful reason why this combination works so well. Steel and concrete have almost identical coefficients of thermal expansion. They expand and contract by nearly the same amount when temperature changes. If they didn't, the reinforcement would constantly be pulling away from the concrete, cracking it from the inside. It's a fortunate coincidence that these two very different materials respond to temperature changes in the same way. Without that coincidence, reinforced concrete wouldn't work, and the modern world would look very different. Today, concrete is the most widely used man-made material on Earth. After water, it's the most consumed substance on the planet, and cement production is responsible for roughly 8% of global carbon dioxide emissions. Finding ways to reduce that is one of the most important materials challenges of our time. But let's come back to the story of understanding. Because while engineers were figuring out how to build with steel and concrete and glass, scientists were simultaneously making breakthroughs in understanding the atomic and molecular basis of materials. And one of the most important classes of materials, one that would eventually rival metals and ceramics in its importance, was barely understood at all until the 20th century. I'm talking about polymers, the long-chain molecules that make up rubber and silk and cellulose and, eventually, the plastics that would reshape daily life in the 20th century. And the polymer story starts with one of the most important and underappreciated materials discoveries of the 19th century, one that nearly killed its discoverer several times over, and one that began with a very sticky problem, literally sticky, because the material in question was natural rubber, and in the 1830s, natural rubber was driving people absolutely crazy. Here's the issue. Rubber, made from the sap of the Hevea brasiliensis tree, the rubber tree, native to South America, had attracted enormous interest in Europe and America. It was elastic. It was waterproof. You could stretch it, bend it, twist it, and it would spring back. In some ways, it seemed like a miracle material, but it had two devastating flaws. In cold weather, it became stiff and brittle, losing all its stretch, and in hot weather, it became soft, gooey, and foul-smelling. Rubber shoes would freeze solid in winter and melt into sticky mush in summer. Rubber-coated raincoats, Macintoshes, named after the Scottish chemist Charles Mackintosh who invented them, would stiffen in the cold and stink in the heat. Companies that had invested fortunes in rubber products were going bankrupt because the material was simply unreliable. Enter Charles Goodyear. And Charles Goodyear is one of the great, tragic, heroic figures in the history of materials. Born in 1800 in New Haven, Connecticut, Goodyear was a hardware merchant who became obsessed, truly obsessed, to the point of ruin, with solving the rubber problem. He had no scientific training, he had no money, he had no laboratory. What he had was an absolutely unshakable conviction that rubber could be made stable, and he spent years experimenting, mixing rubber with every substance he could think of: magnesia, lime, nitric acid, turpentine. He sold everything he owned. His family lived in poverty. He was arrested for debt. His children went hungry. And still, he kept experimenting. The breakthrough came, according to the most popular version of the story, in 1839. Goodyear accidentally dropped a piece of rubber mixed with sulfur onto a hot stove. When he peeled it off, he found that the rubber had changed. It was still flexible, but it was no longer sticky. It didn't melt in heat or stiffen in cold. It had been transformed. What had happened, though Goodyear didn't know it at the molecular level, was vulcanization. The sulfur atoms had formed chemical bridges, crosslinks, between the long, tangled polymer chains of the rubber. Before vulcanization, those chains could slide freely past each other, which is why the rubber was soft and deformable. When they slid apart too easily, the material became gooey. When they couldn't move at all because of cold, it became brittle. But with sulfur crosslinks tying the chains together at intervals, the chains could still flex and stretch, giving the rubber its elasticity. But they couldn't slide completely apart. The crosslinks held the structure together. The rubber was dimensionally stable across a wide range of temperatures. Goodyear patented the process in 1844, but he was terrible at business, and worse at defending his patents. Thomas Hancock in England independently developed a similar process and patented it in Britain before Goodyear could. Goodyear spent much of the rest of his life in litigation, trying to protect his invention. He died in 1860, deeply in debt. The Goodyear Tire and Rubber Company, founded in 1898, was named in his honor, but had no connection to his family. He never profited from the industry his discovery created. But the process he stumbled onto, vulcanization, was the first time anyone had deliberately modified the molecular structure of a polymer to change its properties. It was, in a real sense, the birth of polymer engineering. And here's what's important about that from a materials science perspective. Rubber was the first material that forced scientists to think about a completely different kind of structure. Metals have crystal lattices. Ceramics have rigid ionic or covalent networks. But rubber is made of enormously long, flexible molecular chains, polymers, from the Greek poly, meaning many, and meros, meaning parts. Each chain is thousands or millions of atoms long, coiled and tangled like a bowl of microscopic spaghetti. And the properties of the material depend not just on what the chain is made of, but on how the chains are arranged, how they interact with each other, and whether they're tied together by crosslinks or free to slide. This was a completely new way of thinking about materials, and for a surprisingly long time, many chemists refused to believe it. The idea that molecules could be that big, that a single molecule could contain thousands or millions of atoms, seemed absurd. Throughout the early 20th century, the dominant view was that materials like rubber and cellulose and proteins were just aggregates of small molecules, held together by some mysterious force. The man who proved otherwise, who fought the scientific establishment and eventually demonstrated beyond doubt that polymers are real, very large molecules, was a German chemist named Hermann Staudinger. He proposed his macromolecular hypothesis in 1920, spent 2 decades defending it against fierce criticism, and finally won the Nobel Prize in Chemistry in 1953. He was right. The critics were wrong, and his insight opened the door to the deliberate design of synthetic polymers, plastics, that would transform the 20th century in ways nobody anticipated. The first truly synthetic plastic, a material with no natural equivalent, created entirely by human chemistry, was Bakelite. And the story of Bakelite starts with a Belgian-born chemist named Leo Baekeland, and it's a story about ambition, chemistry, and the surprising way that one invention can cascade into 1,000 applications nobody imagined. Baekeland was born in Ghent, Belgium, in 1863, earned his doctorate at 21, and emigrated to the United States, where he made a fortune selling photographic paper technology to Eastman Kodak. Then he turned his attention to a new problem, finding a synthetic substitute for shellac, a natural insulating resin that was expensive and imported from Asia. He started experimenting with phenol and formaldehyde, a combination chemists had struggled with for decades, because it produced an uncontrollable, intractable mess. Baekeland's breakthrough, achieved in 1907, was figuring out how to control the reaction using heat and pressure. He built a vessel he called the Baekeleizer, essentially a pressure cooker for chemistry, and found that by carefully controlling the temperature, pressure, and the ratio of ingredients, he could produce a material that was hard, heat-resistant, electrically insulating, and chemically stable. He could mold it into any shape before it fully hardened, and once set, it stayed set permanently. You couldn't melt it. You couldn't dissolve it. It was, in the language of polymer chemistry, a thermoset, a material where the polymer chains are so thoroughly cross-linked that the structure is permanently rigid. Baekeland patented Bakelite in 1909, and the material took the world by storm. It was the perfect electrical insulator at a time when the electrical industry was exploding. Bakelite went into electrical outlets, plugs, switches, light sockets, distributor caps for automobile engines, telephone housings, radio casings. It was used for buttons, combs, chess pieces, billiard balls, jewelry, kitchenware, pipe stems, camera bodies. It was marketed as the material of 1,000 uses, which turned out to be an undercount. For decades, if you touched something made of plastic, it was almost certainly Bakelite. And what makes Bakelite important in the history of materials isn't just the material itself, it's the principle it demonstrated. For the first time, chemists had created a new material from scratch, not by processing something found in nature, not by refining an ore or treating a fiber, but by synthesizing something entirely new at the molecular level. Once that door was open, it would never close. The 1920s and 1930s saw an explosion of new synthetic polymers. Polystyrene was commercialized in 1931, a hard, transparent plastic that could be easily molded and was cheap to produce. Polyvinyl chloride, PVC, was developed into a practical material in the late 1920s. Plexiglass, polymethyl methacrylate, appeared in the early 1930s, a transparent plastic that was lighter and more shatter-resistant than glass. Polyethylene, which would become the most widely produced plastic in the world, was discovered more or less by accident at the Imperial Chemical Industries Laboratory in England in 1933, when two chemists, Reginald Gibson and Eric Fawcett, tried to react ethylene gas under extremely high pressure and found a waxy, white solid coating the inside of their reaction vessel. They couldn't reproduce the result at first. It turned out that a tiny trace of oxygen had leaked into the apparatus and acted as a catalyst. When they figured that out and controlled the conditions, they could make polyethylene reliably. But the polymer story I want to spend the most time on is nylon, because it's one of the greatest triumphs and one of the saddest tragedies in the history of materials, and because the person at the center of it, Wallace Carruthers, deserves to be much better known than he is. Carruthers was born in 1896 in Burlington, Iowa. He was a quiet, introverted man, exceptionally gifted in chemistry, and deeply interested in the fundamental science of polymers. In the early 1920s, when he was teaching at Harvard, the DuPont company came recruiting. DuPont was building a new fundamental research division, not product development, not troubleshooting, but pure research. They wanted the best chemists in the country, and they offered Carruthers something remarkable: the freedom to work on whatever interested him, with a generous salary and excellent facilities. Carruthers accepted in 1928, becoming the head of DuPont's Organic Chemistry Research Group in Wilmington, Delaware. Carruthers was fascinated by the polymer debate that was still raging in chemistry. Hermann Staudinger had proposed that polymers were true macromolecules, single, enormous chains of atoms, but many chemists still argued they were just loosely associated clusters of small molecules. Carruthers set out to settle the question by doing something nobody had done before: synthesizing polymers from scratch, building them up step by step from small, well-characterized molecules, so that the structure of the final product would be known beyond any doubt. And he succeeded spectacularly. In April 1930, a member of Carruthers' team, Julian Hill, pulled a lump of a molten polymer out of a beaker and found that it could be drawn into a long, thin fiber. And as he stretched it, the fiber became remarkably strong and silky. The polymer chains, which had been randomly coiled in the molten state, were being aligned by the stretching, lined up parallel to each other like logs in a river, and the aligned chains formed strong intermolecular bonds with their neighbors. This process of stretching and aligning, which became known as cold drawing, was the key to making polymer fibers with useful mechanical properties. The fiber from that first experiment was interesting, but not practical. It melted at too low a temperature and dissolved in common cleaning solvents. But it proved the concept. Over the next several years, Carruthers and his team systematically varied the chemistry, trying different molecular building blocks, tweaking the chain structure, searching for a polymer that would make a fiber with all the right properties: strong, elastic, resistant to heat and solvents, and spinnable into thread. In February 1935, a researcher on Carruthers' team named Gerard Berchet synthesized a new polyamide, a polymer with amide linkages in its backbone, from hexamethylene diamine and adipic acid. It was designated fiber 6,6 because both starting materials have 6 carbon atoms, and when they drew it into a fiber, it was extraordinary: strong, elastic, silky, resistant to heat and moisture. It could be spun into thread and woven into fabric. It was, in nearly every respect, a superior replacement for silk. DuPont recognized what they had. They launched nylon. The name was chosen after extensive internal debate. At the 1939 New York World's Fair, nylon stockings went on sale on May 15, 1940, which the press called N-Day. 5 million pairs sold on the first day. Women lined up around the block. When supplies ran short during World War II, nylon was diverted to military uses, including parachutes, tire cords, and rope. There were actual nylon riots. The material had captured the public imagination in a way that no synthetic material had before, or arguably has since. But Wallace Carruthers never saw any of it. He suffered from severe depression throughout his adult life. Despite his extraordinary scientific achievements, he had essentially founded the field of synthetic polymer chemistry. He remained convinced that his work was worthless. He carried a capsule of cyanide in his pocket, reportedly telling colleagues it was his emergency exit. On April 29, 1937, at the age of 41, in a hotel room in Philadelphia, he dissolved the cyanide in lemon juice and drank it. He died 2 days before his 41st birthday. His daughter, Jane, was born 7 months later and never knew her father. DuPont named their nylon production facility the Carruthers Research Laboratory. His contributions to polymer science are immeasurable. He demonstrated beyond any reasonable doubt that Staudinger was right. Polymers are real macromolecules, and they can be designed, synthesized, and engineered at the molecular level. He created a new material that changed the world. And the field he opened up, the deliberate design of polymers for specific purposes, would produce everything from Teflon to Kevlar to the polyester in your shirt to the polycarbonate in safety glasses to the silicone in medical implants. Let me tell you about a few more polymers. Teflon was discovered accidentally in 1938 by Roy Plunkett at DuPont, who opened a cylinder of tetrafluoroethylene gas and found nothing came out. The gas had spontaneously polymerized into a white, waxy solid. It had the lowest coefficient of friction of any known solid and was chemically inert, resistant to virtually every solvent and acid known. DuPont initially couldn't figure out how to use it because they couldn't get anything to stick to it. The Manhattan Project used it to line valves handling corrosive uranium hexafluoride. After the war, a French engineer figured out how to bond it to aluminum, and the non-stick frying pan was born. The Second World War was, in many ways, a war of materials. Japan's conquest of Southeast Asia cut off 90% of the world's natural rubber supply. The U.S. government launched a crash program to develop synthetic rubber, and within a few years, American plants were producing over 800,000 tons per year, one of the greatest industrial mobilizations in history. The war also accelerated aluminum production for aircraft, new alloys for jet engine turbine blades, and entirely new materials for the Manhattan Project. But perhaps the most consequential materials development to come out of the war years, in terms of its long-term impact on civilization, wasn't a new alloy or a new polymer. It was a new understanding of a class of materials that had been known for decades but poorly understood, materials that were neither conductors nor insulators, that sat in an ambiguous middle ground, and that most scientists had considered curiosities at best, irritants at worst. These were semiconductors, and the story of how semiconductors went from laboratory oddities to the foundation of the entire modern world is one of the great materials stories ever told. So let's talk about what a semiconductor actually is, because the name itself tells you something. A conductor, like copper or aluminum, lets electricity flow through it easily. The outer electrons of the metal atoms are free to roam through the material, carrying charge wherever a voltage pushes them. An insulator, like glass or rubber or ceramic, holds its electrons tightly. They're locked in place, bound to their atoms, and won't flow no matter how much voltage you apply, at least not until you apply so much that the material breaks down entirely. A semiconductor sits between these two extremes. At low temperatures, it's an insulator. Its electrons are locked in their bonds. But give it a little energy, heat, light, or a tiny electrical nudge, and some electrons break free and start to conduct. The material exists on a knife edge between conducting and not conducting, and that knife edge turns out to be the most useful property in the entire history of materials. The physics behind this involves something called band theory, which emerged in the 1930s from the quantum mechanical understanding of how electrons behave in solids. In a crystal, the energy levels that electrons can occupy get smeared out into continuous bands by the interaction between neighboring atoms. There's a valence band where the electrons live at low energy, busy holding the crystal together, and there's a conduction band, higher in energy, where electrons are free to move through the material and carry current. In a metal, these bands overlap. Electrons can freely move from the valence band to the conduction band, which is why metals conduct so well. In an insulator, there's a large gap between the bands, too wide for electrons to jump across under normal conditions. In a semiconductor, the gap is narrow, just wide enough that at room temperature, a few electrons can make the jump. And critically, you can control how many make the jump by adding tiny amounts of impurity atoms to the crystal. This is called doping, and it's the key to everything. Take silicon, the semiconductor that would come to dominate the world. Pure silicon has 4 outer electrons, and in a silicon crystal, every atom shares its 4 electrons with 4 neighbors, forming a perfect network of covalent bonds. No free electrons, no conductivity. But now replace one silicon atom in a million with a phosphorus atom. Phosphorus has 5 outer electrons. 4 of them bond with the neighboring silicon atoms, But the fifth one has nowhere to go. It's loosely bound, easily freed, and it becomes a mobile charge carrier. You've just created N-type silicon, negative type because you've added extra negative charges. Or you could add a boron atom instead. Boron has only 3 outer electrons, so it creates a hole, a missing electron that acts like a positive charge carrier, hopping from bond to bond as neighboring electrons shift to fill it. That's p-type silicon. And when you put n-type and p-type silicon together, you get a p-n junction. This is, without exaggeration, the most important material structure in modern civilization. At the junction, electrons from the n side diffuse across to the p side, and holes from the p side diffuse to the n side, and they neutralize each other, creating a thin region called the depletion zone, where there are no free charge carriers. This region acts as a barrier. Apply a voltage in one direction, and you push carriers across the barrier. Current flows. Apply voltage in the other direction, and you widen the barrier. No current flows. The junction conducts in one direction but not the other. It's a diode, a one-way valve for electricity. Now, the first person to build a practical semiconductor device was actually working with germanium, not silicon. In 1947, at Bell Laboratories in Murray Hill, New Jersey, 3 physicists, John Bardeen, Walter Brattain, and William Shockley, created the first transistor. The story of their collaboration, and the bitter personal rivalries that came with it, is a whole drama in itself. Shockley was the group leader, brilliant but abrasive, who felt he deserved sole credit. Bardeen was quiet, analytical, a theoretical genius who would go on to win 2 Nobel Prizes, one for the transistor and one for the theory of superconductivity. Brattain was the experimentalist, the one with the steady hands who actually built the thing. The first transistor was a crude device. It consisted of 2 closely spaced gold contacts pressed against a germanium crystal, with a third contact on the base. It could amplify a signal, take a small electrical input, and produce a larger output, which is what made it revolutionary. Before the transistor, signal amplification was done with vacuum tubes, which were large, hot, fragile, and power-hungry. The transistor was tiny, cool, rugged, and efficient. It would replace the vacuum tube in almost every application and make modern electronics possible. But the transistor's importance goes beyond what it does. It matters because of what it's made of. The performance of a transistor depends exquisitely on the purity and crystal perfection of the semiconductor material. Even parts per billion of unwanted impurities can ruin a device, and this demanded a level of material purity and crystallographic perfection that had never been achieved for any material in history. The process for producing ultra-pure semiconductor-grade silicon is one of the most remarkable achievements of materials engineering. It starts with sand, silicon dioxide, the most abundant mineral on Earth. Through a series of chemical conversions and distillations, the silicon is purified to about 99.999999999%. 9 nines. For every billion atoms, fewer than 1 is an impurity. This is the purest bulk material produced by human civilization. Nothing else comes close. But purity isn't enough. You also need a single crystal. Grain boundaries in polycrystalline material scatter electrons and degrade device performance. So the purified silicon is melted and slowly pulled into a single, perfect crystal using the Czochralski process. A seed crystal is dipped into molten silicon and slowly pulled upward while rotating, and atoms from the melt attach in perfect alignment, building a cylindrical crystal that can be over a foot in diameter. These silicon ingots are then sliced into thin wafers, polished to a mirror finish, and used as the substrate for integrated circuit manufacturing. And the integrated circuit, the idea of putting multiple transistors and other components onto a single piece of semiconductor material, is another pivotal moment in the history of materials. Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor independently invented the integrated circuit in 1958 and 1959. Kilby's version used germanium and had external wire connections. Noyce's version used silicon and a planar process that deposited all the connections directly on the chip surface, which was much more practical for mass production. Noyce's approach won out, and the planar silicon integrated circuit became the foundation of the modern electronics industry. What followed was Moore's law, the observation made by Gordon Moore in 1965 that the number of transistors on an integrated circuit was doubling roughly every 2 years. This wasn't a law of physics. It was an observation about the pace of materials and manufacturing innovation, and it held for over 50 years. The first microprocessor, Intel's 4004 in 1971, had 2,300 transistors. Today's most advanced processors have over 100 billion. And every step along that exponential curve required advances in materials. New photoresist polymers for lithography, new dielectric materials for insulating transistor gates, new metal interconnects, new doping techniques, new etching chemistries. The semiconductor industry consumes more different materials, at higher purity levels, than any other industry in history. But I want to shift gears now, because there's another class of materials that came into its own in the late 20th century, and it represents a completely different approach to engineering. Instead of making things from a single material, what if you combined 2 or more materials into a hybrid that captures the best properties of each? These are composite materials, and they're everywhere in the modern world, from aircraft to sports equipment to wind turbine blades to bulletproof vests. The concept is ancient. Adobe bricks, mud reinforced with straw, are a composite. Reinforced concrete, as we discussed, is a composite. But modern engineered composites take the idea to a whole new level by carefully controlling the type, orientation, and distribution of the reinforcing material within a matrix. The classic modern composite is fiberglass, glass fibers embedded in a polymer resin. Glass fibers are much stronger than bulk glass because they're too thin to contain the large surface flaws that cause glass to fracture. Embed those fibers in a polymer matrix that holds them in place, and you get a material that's strong, lightweight, and can be molded into complex shapes. But the real superstar of composite reinforcement is carbon fiber. And this is a material that connects back to something we talked about much earlier, the fundamental importance of atomic structure. Carbon fiber is made from long, thin filaments of carbon, each about 5 to 10 micrometers in diameter, much thinner than a human hair. And the reason carbon fiber is so strong comes down to the arrangement of carbon atoms within each fiber. The atoms are arranged in sheets of hexagonal rings, essentially layers of graphene, and these sheets are aligned parallel to the fiber axis. Along the axis, the carbon-carbon bonds are among the strongest bonds in nature, so the fiber has extraordinary tensile strength. Perpendicular to the axis, the sheets are held together by much weaker van der Waals forces, which is why carbon fibers are strong in one direction but not in others. This is why carbon fiber composites are designed with fibers oriented in specific directions. You put the strength where you need it. Carbon fiber composites are used in applications where strength-to-weight ratio is critical. Military and commercial aircraft. The Boeing 787 Dreamliner is about 50% composite by weight, mostly carbon fiber reinforced polymer. Formula One cars, high-end bicycles, wind turbine blades, which need to be incredibly strong and stiff, but also light enough to turn in moderate winds. Tennis rackets, golf club shafts, fishing rods. The Mars rovers carry carbon fiber components. And then there's Kevlar, which has one of the best origin stories in materials history. Kevlar is a para-aramid fiber, a polymer with a rigid, rod-like molecular structure that forms incredibly strong, tightly packed crystalline fibers. It was invented in 1965 by Stephanie Kwolek, a chemist at DuPont. Kwolek had originally planned to become a doctor and took the DuPont job to earn money for medical school, but she found polymer chemistry so fascinating that she stayed. The discovery happened during a project to develop lightweight, strong fibers for tires. Kwolek was working with a polymer solution that behaved oddly. It was thin and cloudy instead of thick and clear, like polymer solutions typically were. Her instinct was that something interesting was happening at the molecular level. When she asked the technician to spin the solution into fibers, he initially refused. Cloudy solutions usually clog the spinneret and ruin the equipment. Kwolek persisted, and the fibers they produced were astonishing. 5 times stronger than steel by weight, stiff, heat-resistant, and capable of stopping bullets. Kevlar became the standard material for body armor, and it has saved thousands of lives since its introduction. Kwolek, characteristically modest, said she was very lucky, though luck favors the prepared and persistent, and Kwolek was both. The 20th century was, in many ways, the century of materials proliferation. In 1900, the palette of engineering materials was limited: steel, cast iron, wood, brick, concrete, glass, rubber, a few non-ferrous metals. By 2000, engineers could choose from thousands of alloys, hundreds of polymers, advanced ceramics, composites, semiconductors, optical fibers, superconductors, shape memory alloys, biomaterials. The range of available properties expanded enormously, and with it, the range of things that could be built, and the pace hasn't slowed. If anything, it's accelerating. Because in the 21st century, materials science is entering a new phase, one where we're not just discovering and characterizing materials, but designing them from the atom up, using tools and techniques that would have seemed like science fiction just a few decades ago. And some of the materials emerging from this new era are genuinely extraordinary. Let's talk about graphene, because it's one of those materials that sounds too good to be true and yet, somehow, is real. Graphene is a single layer of carbon atoms arranged in a hexagonal lattice, 1 atom thick. Literally a 2-dimensional material, a sheet of carbon with a thickness measured in tenths of nanometers, and its properties are almost absurd. Graphene is the strongest material ever measured. Its tensile strength is about 130 gigapascals, roughly 100 times stronger than the strongest steel. It's incredibly stiff, yet also flexible. You can bend a graphene sheet, fold it, and it springs back without damage. It's the best conductor of electricity at room temperature, better than copper. It's the best conductor of heat, better than diamond. It's nearly transparent. A single layer absorbs only about 2.3% of visible light, and it's impermeable to gases, even helium, the smallest atom. The story of graphene's isolation is delightful. In 2004, Andrei Geim and Konstantin Novoselov, 2 physicists at the University of Manchester, used a piece of ordinary Scotch tape to peel layers off a chunk of graphite. Graphite, the stuff in pencils, is just millions of layers of graphene stacked on top of each other, held together by weak van der Waals forces. Every time you write with a pencil, you're depositing graphene layers on the paper. Geim and Novoselov repeatedly folded and peeled the tape, each time splitting thinner and thinner layers, until they had flakes just 1 atom thick. They transferred these flakes onto a silicon wafer and measured their electrical properties. It was startlingly simple. No fancy equipment, no billion-dollar facility, Scotch tape and a pencil. They won the Nobel Prize in Physics in 2010. Now, graphene hasn't yet transformed the world the way silicon has, and it's worth being honest about that. Manufacturing large, defect-free sheets is still difficult and expensive. You can't build an industry on Scotch tape. Real-world applications are coming, but slowly. Graphene-enhanced composites, sensors, flexible electronics. These are in development or early commercialization. The full potential of the material is still being unlocked. But graphene is just one example of a broader trend in materials science, the trend toward designing materials at the nanoscale. Nanotechnology, broadly defined, is the manipulation of matter at the scale of individual atoms and molecules, roughly 1 to 100 nanometers. And at that scale, materials behave differently from their bulk counterparts. Gold nanoparticles, for instance, aren't gold-colored. Depending on their size, they can appear red, purple, or blue, because at the nanoscale, the electrons in the particle interact with light in size-dependent ways. Silver nanoparticles have antimicrobial properties that bulk silver doesn't exhibit to the same degree. Carbon nanotubes, essentially graphene rolled into a cylinder, are among the strongest fibers ever measured, and can be either metallic or semiconducting depending on the angle at which the graphene sheet is rolled, which is a mind-bending example of how structure at the atomic level determines properties at the macro level. Let me tell you about another class of modern materials that I find genuinely thrilling. Shape memory alloys. These are metals that can remember their original shape and return to it after being deformed. The most common one is nitinol, an alloy of nickel and titanium, developed in the 1960s at the Naval Ordnance Laboratory. That's where the name comes from. Nickel-Titanium Naval Ordnance Laboratory. Bend a nitinol wire into a paperclip shape at high temperature, then cool it down, and you can straighten it out, twist it, deform it into any random shape, but heat it back up past a critical temperature, and it snaps back to the original paperclip shape. Every time, it remembers. The mechanism behind this is a type of crystal structure transformation called a martensitic transformation, the same word, martensite, that we encountered when talking about quenched steel, and it's the same underlying phenomenon. At low temperature, nitinol has a crystal structure called martensite, which is relatively soft and can be deformed by twinning, a process where portions of the crystal flip their orientation along mirror planes, accommodating the deformation without breaking bonds. At high temperature, the crystal structure transforms to austenite, which has only one stable configuration, the original shape. So heating the deformed martensite causes it to transform to austenite, and the only austenite configuration available is the memorized shape. The material has no choice but to return to it. Shape memory alloys are used in medical stents, collapsed tubes that are inserted into blood vessels and then warm to body temperature, expanding to their remembered shape and propping open the artery. They're used in dental braces, nitinol arch wires that apply a gentle, constant force as they try to return to their memorized straight shape. They're used in spacecraft components, in fire safety valves, in eyeglass frames that spring back to shape after being sat on. And while we're on the subject of metals with remarkable properties, let me mention superalloys, because they represent one of the most demanding applications of materials science in existence. A superalloy is a metal designed to maintain its strength, resist corrosion, and survive at temperatures that would destroy ordinary materials. The primary application is in jet engine turbine blades, and the conditions inside a jet engine are brutal. The gas temperature entering the turbine section of a modern jet engine can exceed 1,500 degrees Celsius, well above the melting point of the blade alloy itself. Think about that. The blades are operating in gas that's hotter than their own melting point. They survive because of a combination of extraordinary materials engineering, sophisticated nickel-based superalloys, with carefully controlled compositions of up to a dozen alloying elements, internal cooling channels that pump cooler air through the hollow blade, and thermal barrier coatings, thin layers of ceramic applied to the blade surface that insulate it from the hottest gas. But perhaps the most remarkable aspect of modern turbine blades is how they're manufactured. Each blade is cast as a single crystal, not polycrystalline, with random grain boundaries that could serve as weak points and crack initiation sites. A single, continuous crystal, grown carefully in a mold through a controlled solidification process. The mold is heated in a vacuum furnace, filled with molten superalloy, and then cooled from the bottom up, so the crystal grows slowly upward through the blade shape. A grain selector, a narrow, corkscrew-shaped channel at the base of the mold, ensures that only one crystal orientation survives and grows into the blade. The result is a turbine blade that is, in its entirety, one single crystal of a nickel superalloy. It has no grain boundaries, no weak points, no preferred directions for crack propagation, and it can survive thousands of hours spinning at over 10,000 RPM in gas temperatures that would melt it if the cooling failed for even a few seconds. Each one of these blades costs tens of thousands of dollars to manufacture. A single modern jet engine contains dozens of them, and your safety, every time you fly, depends on the materials science that went into making those blades. Let me shift to something completely different now, because the frontier of materials science isn't just about making things stronger or harder or more heat-resistant. Some of the most exciting developments are in materials that are designed to interact with living systems, biomaterials. These are materials engineered to work inside the human body. Artificial joints, heart valves, dental implants, drug delivery systems, tissue scaffolds. The challenge of biomaterials is unique. The material needs to be biocompatible. It has to exist in intimate contact with living tissue, without being rejected, without releasing toxic substances, without degrading in unexpected ways. The human body is warm, salty, and full of immune cells designed to attack foreign objects. Titanium is the gold standard for orthopedic implants because, like chromium in stainless steel, it forms a self-healing oxide layer that protects it from body chemistry. Its stiffness is closer to bone than steel's is, which matters because overly stiff implants cause the surrounding bone to weaken from lack of mechanical loading. But cutting-edge biomaterials go far beyond passive implants. Researchers are developing biodegradable polymer scaffolds that cells grow on and then dissolve away, drug delivery nanoparticles that target specific cell types, and bioactive glass that forms a chemical bond with bone tissue, actually integrating with the body. And then there's a category of materials that I find particularly enchanting because they challenge our most basic assumption about engineering materials, the assumption that damage is permanent. Self-healing materials. Materials that can repair themselves when cracked or cut, the way skin heals after a scratch. The first major demonstration of this concept came in 2001, when a team led by Scott White at the University of Illinois created an epoxy composite containing tiny embedded capsules filled with a liquid healing agent. When a crack formed in the material, it ruptured the capsules, releasing the healing agent into the crack, where it reacted with a catalyst also embedded in the material and polymerized, solidifying and bonding the crack faces together. The material healed itself, not perfectly, but substantially, recovering about 75% of its original fracture toughness. Since then, the field has exploded. Researchers have developed self-healing polymers based on reversible chemical bonds, that can reform after breaking. Self-healing concrete that uses embedded bacteria, real living bacteria, encapsulated in protective capsules that activate when water enters a crack, consume nutrients co-embedded in the concrete, and produce limestone that fills the crack. Self-healing coatings for metals and paints. Even self-healing metals, where specific microstructural features allow nanoscale cracks to close at elevated temperatures. And I want to mention one more class of materials before we start to wind down, because it represents perhaps the most conceptually radical idea in the entire field. Metamaterials. These are materials whose properties come not from their chemical composition, but from their physical structure, from the geometry of tiny, repeating units that are engineered to interact with waves in specific ways. A metamaterial for electromagnetic waves might be made of ordinary copper and plastic, but structured into patterns much smaller than the wavelength of light, creating a material that bends light in ways no natural material can. The most famous example is a material with a negative refractive index, bending light the wrong way. First proposed by the Soviet physicist Viktor Veselago in 1968 and demonstrated experimentally in 2000, negative index materials open up bizarre possibilities, including lenses that could resolve details smaller than the wavelength of light. Metamaterials have even been proposed as the basis for electromagnetic cloaking, bending light around an object to make it invisible. The key idea, that engineering structure at a scale smaller than the target wavelength creates properties that don't exist in nature, is profound. Properties aren't just determined by atoms and bonds. They're determined by geometry, by architecture, by design at multiple scales. And that, in a way, is the perfect place to start wrapping up, because it brings us full circle to where we began. Remember those first Stone Age tool makers, 3.5 million years ago, who looked at a rock and saw not just a rock but a shape waiting to be revealed? They were, in their own way, doing exactly what a metamaterials researcher does today, taking the stuff of the earth and imposing structure on it to create new properties. The scale has changed, from hand-sized rocks to atomic-scale lattices. The understanding has changed, from pure intuition to quantum mechanics. The tools have changed, from hammerstones to electron beam lithography. But the fundamental human impulse is the same. Take a material, understand it, shape it, make it do something new. And as you lie there tonight, every single thing around you is a testament to that impulse. The steel in the springs, or the frame of your bed, forged from iron ore and carbon, heat-treated and alloyed, its crystal structure carefully controlled. The foam in your mattress, a polyurethane polymer with a specific cell structure designed to compress under your weight and slowly spring back. The cotton or polyester in your sheets, one a natural cellulose fiber, the other a synthetic polymer, both processed and woven into fabrics with specific textures and strengths. The glass in your windows floated on liquid tin to a perfect flatness. The copper in the wires running through your walls, drawn from ore that was smelted in a process not so different from what those first accidental metallurgists did 7,000 years ago. The silicon in every chip, in every device in your home, purified to 9 nines and grown into perfect single crystals. Every one of these materials has a story, a history of discovery, of accident, of dogged experimentation, of theoretical breakthrough, of people who looked at the world and asked, "What is this made of? Why does it behave this way? And can I make it better?" That question, "Can I make it better?" is the engine of materials science. It's what drove the first bronzesmith to mix tin with copper. It's what drove Bessemer to blow air through molten iron. It's what drove Goodyear to keep mixing sulfur into rubber after everyone else had given up. It's what drove Carruthers to build nylon, molecule by molecule, in a quest to understand the nature of giant molecules. It's what drives researchers today to stack atoms into structures that bend light backward and build crystals that heal their own cracks. And the beautiful thing is that we're nowhere near the end. The periodic table has 118 elements, and the number of possible combinations, alloys, composites, and structures you can make from them is essentially infinite. Every year, computational tools discover new material compositions that no one has ever synthesized. Machine learning algorithms now screen millions of hypothetical compounds for desirable properties, guiding experimentalists toward the most promising candidates. The old model, stumble onto a material, test it, figure out why it works, is being supplemented, and in some cases replaced, by a new model, predict what you want, design it on a computer, and then make it. Materials by design rather than materials by accident. But even as the tools change, the fundamental challenge remains the same one that faced those first toolmakers in the Rift Valley. You have to understand the material. You have to respect what it can and can't do. You have to work with the physics, not against it. And you have to keep asking questions, because every answer leads to 10 new ones. So as you settle in, as your breathing slows and the day fades, here's maybe the most comforting thought I can leave you with. The world is made of materials. Every atom, every grain, every fiber and crystal and amorphous tangle of polymer chains, the calcium phosphate in your bones, the iron in your blood, the collagen in your skin. You are made of materials too. And those materials, all of them, from the simplest stone to the most exotic metamaterial, obey the same laws of physics, the same atomic bonds, the same thermodynamics, the same quantum mechanics. The universe is consistent, and the materials are its language, and we have spent 10,000 years learning to read that language, and we're still learning, and there's so much more to discover. And right now, the materials are doing what they've always done. The atoms in the steel of your bed frame are sitting in their body-centered cubic lattice, vibrating gently with thermal energy, each one held in place by the metallic bonds it shares with its neighbors. The polymer chains in your mattress are coiled and tangled, flexing and relaxing under your weight. The van der Waals forces between them, giving the foam its slow, gentle spring. The glass in your window is holding its ancient, disordered structure, atoms frozen in the random arrangement of a liquid that cooled just a little too fast to crystallize. Everything is in its place. Everything is doing what materials do, holding together, supporting, protecting, insulating, conducting, existing, quietly, reliably, the way materials have existed since long before anyone was around to wonder about them. The world figured out materials about 4.5 billion years ago, when iron sank to the core and silicates formed the mantle, and everything sorted itself by density and chemistry into the layered, differentiated planet we live on. We just showed up recently and started paying attention. And now you know a little more about what we found when we did, what those early toolmakers discovered when they struck two rocks together, what the first smelters learned when copper ran shining from a furnace, what Bessemer and Brearley and Carruthers and Quolick and 1,000 other curious, persistent, often lonely people figured out, one experiment at a time, one material at a time. That's a good thing to carry into sleep. The knowledge that every material around you has been understood, shaped, and placed there by the accumulated effort of thousands of years of human curiosity. That the pillow under your head is not just a pillow, it's a triumph of polymer chemistry and textile engineering. That the roof over your head is not just a roof, it's the culmination of 10 millennia of structural materials development. that you are surrounded, cradled, held up by the materials that humanity learned to master, one discovery at a time, across the long, slow, beautiful arc of history. So let that settle. Let the ideas drift, and let the materials do what materials do best. Support you, quietly, steadily, as you close your eyes and let the warmth of the blankets and the softness of the pillow and the gentle weight of the world carry you, slowly, gently, reliably, into sleep.